Good morning. Today we're going to look at our very last topic of our geometry unit. And this basically involves general conics. And it'll even require us to use some of the things we first looked at way back in linear algebra. So it's a kind of a nice culmination of the linear algebra / geometry units. To start, we have an equation up here on the board involving what we could call a general conic. Now, you already know a lot about the conics. We've just completed some problems involving conics in terms of parametrics. And the main reason for that is many conics are not technically functions. So when working with the graphs, it's nice to write them in terms of parametric form. We can also have a parametric form of working with tangents and normals. So that's some of the more advanced stuff we've done up to this point with conics. Not to even mention some of the most basic stuff that you've seen probably in previous courses. Why they're conics, the locus definition of the conics, and of course all of the characteristics of our big four conics. In terms of this general conic equation, there's one term that really causes the issue, and that's this xy term. We already know that without that xy term, that we have all of these terms involving either x or x squared, y squared, x or y, and constant, depending on which terms are present and what the coefficients are, we can quickly identify the conics. So just maybe as a recap. First of all, if there's only an x squared or a y squared, we know it's a parabola. And then we could write that parabola in nice vertex form or user-friendly form and know a lot about its characteristics. If the coefficients of the x squared and y squared are the same, then we can identify this as a circle. And then, of course, we can use algebraic methods to complete the square and rewrite it so we know the center of the circle and the radius. If these are both positive but not the same, then it's an ellipse. And that's really why we can consider a circle as a special case of an ellipse, still in the same general format. And again, we would do some algebra to be able to rewrite it in a nice form so it can identify easily the center, the foci, the vertices, the endpoints, the minor axis, major axis, all of the important characteristics of an ellipse. If these are opposites, meaning one positive and one negative for the x squared and y squared term, then we know it's hyperbola. Same thing, change it a little bit so we can identify all the important characteristics of hyperbola. All the while, we can sometimes identify it as one of those big four and then change it into the parametric version and then do some of this stuff with the parametrics. But today we're going to take a look at what happens when we do have that xy term. And I'm going to split this video into two parts. One, kind of the outline of how we go about solving some of these problems. And then one is going to be a big full example of doing just that. So let's see what we have up to this point. What this xy term does. It's basically going to tell us that we're going to have a conic, but there's going to be a translation. Maybe, because we can already translate conics up, down, left, and right. And this is the biggest thing, a rotation. So when we see this xy term, we basically have a conic that is not considered either horizontal or vertical. Now, for a circle, it's not going to be as big a deal. But for the others, that's going to be much different than what we've seen before. One thing that you might want to do is a little activity. It's on page 223, investigation 4. All right, if you use Desmos or any other type of quick software that can help, that will allow you to graph all sorts of functions, it's kind of neat. Just graph these. You start to notice some things, even though I'm going to tell you those details about different conics. because it's not going to be as simple as if these two are both positives that we automatically know it's going to be an ellipse or a circle. That's going to have something to do with it. So it's a neat little activity, but if you have a quick little way to graph these functions, you can start to get a feel for what they should look like. But one of the biggest things about these conics is we are able to put them in what we call quadratic form. Now, quadratic form involves matrices. So here would be an example of quadratic form for this very conic. I'm going to let X be the matrix simply XY. And then A is going to be the matrix A, B, B, C. And then I'll use a matrix V to be the other two, D and E. The constant can always be thought of as just a constant. We don't need to put that in any matrix form. So basically what I can do then is I can write this equation differently. I can write this equation as X transpose A, and then you could turn right around and multiply it by X, plus B transpose X, plus, again, that constant, whether it's in matrix form or normal form, it's going to be the same. So this is what we can consider quadratic form for any type of a conic. Now you might wonder why. How is that going to help us? Well, before I get to these steps of how it's going to help us, just remember a few things. Is that putting something in a matrix is a nice way to help us understand certain transformations. Translation, yes, but that can be done maybe other ways, but this rotation is huge. So if we identify a rotational matrix from this, I can figure out the angle of that rotation. So that's really what a lot of it comes down to. So here are some guidelines to transform a general conic to standard. Now, what we mean by that standard, again, is kind of that user-friendly form. If we know it's a parabola, or sorry, maybe an ellipse, it might be like x minus 2 squared over 9 plus y minus 3 squared over 16 equals 1. That would be considered a general form, or sorry, a standard form, because it's very easily identified and we know all of its characteristics very, very quickly. So we somehow want to take this and put it in that form. And again, because of this xy, we have a little bit of an issue. So here are some of the steps. First thing, you're going to rewrite in that quadratic form. Now I'm not going to do that, but that's basically rewriting it this way. And that won't be too difficult. And here's a blast from the past in terms of linear algebra. We are going to find the eigenvalues and eigenvectors. Now we're going to typically call these lambda 1 and lambda 2. Okay, comment there, kind of hard to see. Right, next we are going to use the normalized eigenvalues as column matrix of matrix P. I'm going to say we're going to create P, which is going to be a matrix by the normalized eigenvectors. As columns. Now normalized, remember, means basically it's a length of 1 if you want to think of it as a vector. And we do want this determinant, of course, also to be 1. And then the final piece, which is where a lot of the work comes in, is to let x equal p x prime. Where x prime is basically x prime y prime. Now what would happen here is this is really going to be this capital value, okay, that we have. And by making that substitution, we would basically end up with a interesting version, so we can identify it, we have it in standard form, and we know everything about it, how this has been changed. Now a couple of the things to recall, that in terms of this p-value here, remember that if we have cosine theta, negative sine theta, cosine theta, that's basically a rotation matrix. So if we have this rotation matrix that we get from this P and we identify it, we would know basically what the rotation is. Now many times what these values are would lead us to a rotation of a pi over 4, pi over 6, something very clear. Other times the best we might do is just say it's going to be an arctangent of a number. We can still get a feel for that, but we can write it as an exact value if necessary. One other thing about this, remember that if we have P transpose AP, that's basically going to be your matrix with the eigenvalues along the main diagonal and zeros for the other place. The reason that's being is P is orthogonal. So here's the information. We know the general conic has this XY term. That's going to lead to translations or rotations. This activity will help you kind of maybe start to make some sense about how you can make that prediction, and we'll sum that up in our next short video. But really what it comes down to is this. We want to be able to take a matrix in general form and put it into this quadratic form. That will then allow us to find eigenvalues of A. Those eigenvalues, or eigenvectors, will be the columns of P once we normalize it, and then we're going to be able to make the substitution. And after that, a ton of algebra to rewrite it. That's it. In a few minutes, I'll produce the second video involving an example of what exactly this all means.